in here. All right. Well, today our topic is the Nelder-Mead method. This is an optimization method, a numeric method for finding a minimum of some kind of function. This is used in multi-dimensional settings. So on Monday, we introduced coordinate descent as a way to approach multi-dimensional problems. Nelder-Mead's another one. Nelder-Mead is what we call a direct search method, okay? I have to give credit to Professor Gavin from Duke University, produced some notes that were very helpful. Anyway, we use the Nelder-Mead method to find the minimum of a function. And what it does is it basically evaluates the function at a few locations, and the algorithm says, well, why don't we try out another location, okay? And based on the value it finds at that location, it kind of searches for other things. So it's kind of just like, based on these locations, let's try out another location, and it just keeps going until it finds it can't find any values that are lower, basically, okay? It doesn't use derivatives, doesn't use other kinds of things to figure it out. It just directly searches for values. Okay, the search method works well, but is not guaranteed to converge. So that's something to keep in mind. Okay. The way it works is it uses what we call a simplex. Okay, so a simplex is basically like a triangle, but in higher dimensions as needed to be. So it's a shape consisting of n+1 vertices if you're in n dimensions. So if you're in 2 dimensions, a simplex is a shape with 3 vertices, basically a triangle. Okay, if you're in 3-dimensional space, then a simplex has 4 vertices, and basically you get this little pyramid thing, and you call that a tetrahedron. So it's like a pyramid, but every side is a triangle. So not that's a tetrahedron. Okay, in 4-dimensional space, you have what's called a 5-cell or a pentachron, and it's kind of the 4-dimensional version of a tetrahedron. Okay, and it looks kind of like this. You've got in 4-dimensional space, you have 5 vertices, and this vertice that looks like this is just a 3-dimensional shadow. Okay, 3-dimensional shadow of the thing, and this is what pentachron looks like when it's rotating, when its shadow is rotating. This fifth dimension, this 5th vertice kind of moves about in the thing. Okay, this is it can be kind of unfolded into these things. But anyway, that's what a simplex is. And so as far as the illustration goes, we will use a triangle. I'll do 2-dimensional space, and we'll have a triangle as far as their simplex goes. But all of these things can be basically extended into higher dimensional spaces using a higher dimensional simplex. Right? And so we have some kind of function that takes in these values, and so we're using a 2-dimensional function. And what we want to do is our goal is to find a local minimum. And so we start with just this arbitrary triangle, 3 arbitrarily selected points. So maybe you have an arbitrary selected point, and then you go up in the x direction and up in the y direction or something to form your simplex, to form your little triangle here. If you're in a higher dimensional space, you just kind of go, you can just start at some arbitrary location and then, add 1 to each of the different dimensions or something, okay? And then the methods, the steps are sort, and then you'll do one of these 4 things: reflect, extend, contract, or shrink, okay? And then after you do that, you'll check for convergence, and then you repeat. And at each iteration, you'll do one of these 4 actions, okay? You'll check for convergence, and then you start off by kind of sorting the points. So we will, the very first step is to evaluate the vertices. Okay, so here I've got 3 vertices, and we evaluate the function at the 3 locations, and we sort them from best to worst. Best is the point that has the lowest value, and the worst is the point that has the highest value. So f of u is the best point, f of w is the worst point. And so whatever your 3 points are, you're going to label them, u, v, and w. And so we will say w is our worst point, okay? So u is our best point, and w is going to be our worst point. And so now that we've ordered all of these things, we will begin doing the moves here, okay? So we have the first thing we can do is we can try a reflection. And so what we will do is we take the worst point and we reflect it through the centroid of the remaining points. So here, u and v are our 2 remaining points. And basically the centroid is going to be this point right here in the middle, okay? Maybe I'll call that M. And we're going to reflect W through M. So basically you can take a little vector. This is going to be WM. And then, you would add that onto here, okay? And you get WM again. And that's going to be R, okay? So you reflect the worst point through the centroid into and you get your reflected point. Okay. If you have a tetrahedron. Okay, so let's say this is what you have, and let's say this is our worst point. This is our W, okay? And then you have these, then you find the centroid, right, of these 3. This is the centroid here of the remaining points, and then you will reflect this through the centroid. And so so imagine basically you have this pyramid, this tetrahedron, and then you reflect it through. And so you would end up probably over here. Okay. And this would be the W gets reflected through the midpoint there. So here, the midpoint is this just this one location here. But again, in higher dimensions, if you have some kind of tetrahedron, all right, you find your worst point, you take the midpoint of the other points, all right, or the centroid of the other points, and you reflect it through that. Okay. And so this would be our reflected point, R. And then you find the cost of the reflected point. And if this point is better than V, right? So remember, this is number 1, this is number 2, this is number 3. And if this point outperforms V, then great, okay? If it's better than V but not U, then we say, okay, you know what? We don't want to go too far, so we will accept this point. Okay. If here, let me delete some of this notation here. And I'll just redraw all of it, but that's fine. Okay. If R is even better, right? So if R outperforms the best point, so this used to be the best, second best, and worst point. If R is even better, this becomes the new number 1. Then we try to push our luck a little bit, and we say, what if we extend it? Okay, we just try to be a tiny bit greedy. And we say, well, you know what? Maybe we're getting better performance here. Let's keep trying to go in this direction. All right, and then we'll try the extended point. And basically, you can think of this as if from W to M, if I've got some vector WM, Then R is going to be my midpoint plus WM. And then I can kind of go the same distance from here to here again, right? So E would be 3 times WM, or I can think of the reflected point plus WM as well, okay? So you just think of like, okay, what's the distance to this midpoint? And then we just add another vector in that direction. And then we evaluate the cost at E as well. So, we're going to try out R, we try out E. And if f of E is even better than the reflected point, then we're going to take it, okay? But then we'll stop. We're not going to keep pushing our luck and try another extension or anything like that. We just say, hey, what's the cost at the extended point? If it's even better, like we're getting better performance, then the reflected point will take that. And we will replace W with E. And then, that becomes our new best point. And then currently V will become the worst point, okay? If the extended point is not better than the reflected point, then we'll just take the reflected point, okay? And this will still be kind of, this will be the point that we take, and then V will be our worst point. If we reflect the point, okay, and so, this is, again, our best point, our second best point, and our third best point, and if we reflect it, and if R is not better than V, okay, if this is still like our third best point or something, there's no point in accepting the reflected point, because then that will just become the new worst point, okay? And you would reflect it back and you'd just be flipping between R and W, because in W is the worst point, you reflect it, and if R is the worst point, then how are you going to improve anything? So when we reflect any of these points or we try a new point, it needs to outperform the second best point. Okay, it can't just become the worst point again. So it needs to at least outperform the second best point for you to kind of to make an improvement. Okay, so in this case, if R doesn't outperform V, then we will try out two contracted points, okay? We have the inside contracted point and the outside contracted point. You can think of the inside contracted point as 1/4 of the way between W and R, and you can think of the outside contracted point as 3/4 of the way between W and R, right? And we'll evaluate the function at the inside and the outside contracted locations. And if either of those outperforms V, then we will replace it. We will replace W with the inside or outside points, and we'll take whichever one is better. And then we would check for convergence. Okay. And then if none of those do any better, okay. So you tried the reflection, you tried the reflection, it doesn't work better. You try the contractions, they don't work better. Then we are going to just shrink the entire simplex towards U. U is the best performing point, and we say, you know what? We tried all of these things, none of those got better. So what we'll do is we will just shrink the simplex towards U, and so we'll go from W to W prime. W prime is going to be a point halfway between U and W, and then we'll replace V with V prime, where V prime is a point halfway between U and V. And that's that. And then after that, after you have your new simplex, you check for convergence. There's a few methods. It's a little bit trickier because you got multiple points. But basically, you just want to kind of see, are we reaching a point where things aren't improving, things are, remaining exactly the same in all of these cases here. Okay. And that's that. Let me go ahead. I'm going to go ahead and just give you the view quiz answers. Sorry, view quiz. And all three answers go A, B, and C. Okay, question 1, question 2, in question 3. That's your review quiz answer. We'll have that. Okay. Let me show you an animated demo of the Nelder-Mead algorithm. Okay. So this is a little animation I made, and this is the function. Okay. So the function has these contour lines, and the optimum is somewhere in this bottom region here. And we have these contour lines where you can see, basically the more contour lines you have to cross from the center, the higher up you are. Okay. And so we'll start off. This will be our starting simplex, 0, 0, 1, 0, and 0, 1. Okay. And so from this thing, we can see this is our best performing point. It's the fewest kind of contour lines away from the center. All right. And then these 2 points are both pretty bad. And we ask the computer to evaluate, and it labels what it's going to do is it's going to label the worst performing point in red. With each simplex, it'll label the worst performing point in red. So this is my W. And so the first thing I'm going to do is I'm going to try reflecting W across the midpoint of the 2 remaining points, and we get this, okay? And what we need is we need the reflection to outperform at least the second best point. And we can see, it certainly does, okay? And this reflection outperforms the second best point, and it also outperforms our best point, right? Our best point is past this contour line, and this one is inside the contour line. So this one actually outperforms it. So because the reflection outperforms the best point, we will try being a little bit greedy, and we will try extending it, okay? So when you extend it, it takes you to here. We evaluate that. We look at the extended point. We say, oh yeah, that's even better than the reflected point. And so in that case, we will accept the extended point. So to show that we've accepted that point, I'm going to color it in green. And then this will be, we'll get rid of the red dot, and my new simplex will be the 2 blue dots and the green dot. Okay, so here's my new simplex. Now I look at this simplex and I say, which is my worst point? The worst point is this one right here. This is the farthest away. We had to cross the most number of contour lines to be out here. And so I'm going to try to reflect it across the midpoint of the 2 other points. Okay, so red is the worst. We reflect it, and it ends up here. And so looking at this, I say, is it better than the second best point? Yes, it is better than the second best point. Is it better than the best point? Okay, and we could see the best point is on the inside of this contour line, and this yellow dot is outside the contour line. So it is better than this, which is good. It's not better than that. So we're not going to bother trying to extend it. We're just going to accept this point as the next thing. Okay, so that becomes green. We accept that, and this becomes the next simplex. So this is my best point, second best point, worst point. I'm going to try reflecting the worst point across the midpoint here. And that takes me to there. And we can see, oh, you know what? This is better than that. It's better than the second best point. It's better than the best point. Okay, it takes me to right here. We're basically only 2 contour lines away from the center. And so I'm going to try pushing my luck, and I'm going to try extending it. But when I extend it, it's not better than just the reflected point. So we're going to accept the reflected point. And this becomes my simplex here. This is my worst point now. I'm going to try reflecting it, okay? When I reflect it, we can see it is better than that point, and it is better than the second best point, but it's not better than my best point. So I will just accept it. I'm not going to try extending it, okay? This is now my worst point here, and I will try reflection, okay? This reflection, well, it's hard to tell. Is it better than this? The second best point, maybe, maybe not. It is, and so I guess we take it, okay? So this is now my worst point. I will try reflecting it. Okay, and when I reflect it, what happens? I end up out here. This reflection is not is worse than this point. Okay, so I end up getting worse performance. So the reflection is not better. And so what I need to do is I need to try some contracted points. So I'm going to try the outside and the inside contracted points. And we can see the inside contracted point, this one right here, is better than that one. This one's closer to the center. And so we'll do that. Okay. And with this, we can see this is now our worst point. So I will try reflecting it. Reflecting it gives me worse, it gives me better performance than the red dot, but not better performance than the other two. So we are going to try contracting. Okay. And so I contract, I get this point and this point, and the green one is the best. So we'll take that. Okay, so this is my next simplex. This is the worst point now. I will reflect it. Not any better. I try contracted points, and we can see this green contracted point, that's going to be the best. So my simplex keeps getting smaller now. Okay, this is the worst point. I will try reflecting it. It's not worse. I try contracted points. I'll take the inside contracted point. Okay. In this case, that one's the worst. We try reflecting it. Reflecting doesn't improve. I try the contracted points, and I will take that. Here's my thing. This is, I reflect it. And in this case, the reflected point is better than the other two. And so I try extending it, and then we say, okay, extending doesn't work. So I just take the reflected point. Okay, that's the worst. I try reflecting it. I try contracted points. We end up getting that one right there. And, we just kind of, we reflect, contract. This is my triangle, and this is, and we just kind of keep going, all right? And then, and I think this is where it ends. So let me just kind of play it all the way through without me interrupting and pausing. You can see the Nelder-Mead algorithm, okay? Starting with a simplex, we reflect, extend, we take the extension, reflect, we take the reflection, we reflect, we extend, but we take the reflection, we reflect, take the reflection, we reflect, take the reflection. Now we contract, we try the reflection, again we contract, we take the reflection, we'll take the inside contracted point, take a reflection, we'll take the inside contracted point, keep going, and then we end up with the inside contracted point, and then we'll take the reflected point, we take the inside contracted point, and we kind of keep going. And you can see the simplex gets smaller as it hones in on where kind of the local min on this function would be. Okay, and that is that's the Nelder-Mead algorithm there. Okay. This is it's popular. It is in R. R has a numeric optimization function called optim, and you can choose a variety of algorithms. The default optimization algorithm is the Nelder-Mead method, and so so it is a popular method as far as numeric optimization goes. Okay, I think I gave you your view quiz answers. So we will wrap it up there, and that will be it. Have a great rest of your day. I'll have office hours later at 10:30. Otherwise, we'll see you on Friday.